First things first, I don't know if Welch ever told you guys this, but I think you ought to know how or why vectors are drawn like that and that. So, if you imagine an arrow, like the kind you shoot people with, then, there's a stick, there's like feathery bits, and then there is a point. So if you are looking at the arrow head on, like it's about to hit you in the face, you will see the point of the cone, which looks like that. If the arrow is flying away from you, so you see its tail, then you see the feathers at the end, which will look like that. So the X is a vector pointing into the page, and the dot is one pointing out. Alright. Then we have the right-hand rule, first right-hand rule of many. So let me just take one of these. Alright, so this is the right-hand rule. You'll hold your you hold your index finger and your thumb in like a finger gun pose, and those can never ever move. Then your middle finger can come out and swing anywhere you want it to go, really. So it can be pointing more like in this direction or more in this direction. That's all fine. But in any case, your index finger is your first vector. Your middle finger is your second vector. And your thumb is the result. So we can call this, I don't know, A. So then you have A is equal to V cross U. So if you look on the Physics C formula sheet, the one you get on the test, I will quickly insert a part of that here. That's everything that's relevant for today. So if you look at that formula sheet, you'll see they give you some of the stuff in terms of cross products. So for example, this here, the magnetic force from, or rather on a moving charge, you can see it's V cross B. So you would point your index finger in the direction of the charge's velocity, and then your middle finger in the direction of the B field, and your thumb would give you the force. Alright, so from there, let's talk about the field of a permanent magnet. So this is going to be pretty quick. So simply, you have north and you have south, and the field lines go from north to south. They should be more or less perpendicular to the magnet where it touches, and then they will loop around. Magnetic field lines should always, always, always form loops. So, I don't know, something like this. Nope, not that way. And they will point from north to south. Only weird thing to remember here, if you get questions asking about Earth's North Pole, so that's the Arctic, is magnetic south. So that's a little backwards, but that's just something you might want to remember. Alright, so then in general, when you get, let's see, so when you have two permanent magnets close together, such that their field lines will be touching, whenever they point in opposite directions where they touch, so like here, they're pointing in opposite directions, the magnets will attract, and if they point in opposite or if they point in the same direction, so if the north and south were flipped on this bottom magnet, then they will repel. Okay, so that's permanent magnets. They shouldn't show up too much on the test. So now let's move on to the fun stuff. So first of all is magnetic field from a point charge. Oh, by the way, pipe up whenever you want if you have a question. Magnetic field from a point charge. So a moving point charge produces a magnetic field, and the... Ooh, actually, hang on. I will do this in a different order. Let's look at how magnetic field affects a point charge. So magnetic field will produce a force on a moving point charge. So let's say we have a uniform B field pointing into the page. So this is the B field. And then we have a little charge Q moving with some velocity V to the right. So straight from the formula sheet, the force, magnetic force, is going to be equal to QV cross B. So here, if you use your right-hand rule, you should find that the charge is going to, or the experience of force pointing up. So the charge is only going to experience a force as long as it's moving perpendicular to the B field. That's just because of how the cross product works. So as long as it is moving perpendicular to the B field, so in this case it's moving in the plane perpendicular to the B field, it's going to move in a circle if left alone, if it stays in the B field, because it's going to always be experiencing this force perpendicular to its motion. So we can imagine it deflects upwards a little bit, and then once it's over here, if it has velocity pointing this way, that's going to have a force pointing this way, and so on and so forth as it goes around the circle. So you can actually find how big of a circle it makes just by using circular motion stuff. So we know centripetal force is equal to V squared over R times M. And if we just set that equal to our magnetic force, QV cross B, then we can find that, ignoring some vector stuff, that the radius of the circle is equal to M over QB. So as the mass of the particle increases, the radius is going to increase, and as charge or as the B field strength increase, the radius will decrease. Alright, so that is the effective field on a point charge. Now let's look at the effect of a field on a wire. So this can be derived straight from the above. So let's say we have some wire carrying current off to the right, and it's in a uniform B field. So we already know from above that FB is equal to QV cross B. Now if we rearrange a little bit, then we find this is the same thing as Q, let's see, we can call it L, I suppose, over S cross B. I'll just ignore the vector stuff for now. We can worry about that later. So charge, Is this supposed to be? It's supposed to be a T, I guess. So charge over time here, that's just current. So then we find this. So, I guess this is the way you'll see it in the formula sheet. L cross B. So L just points in the direction of current flow, just like by convention. The L is the vector instead of the I, but it's the same thing either way. So the L is just the length of the current that is actually in the B field. So if this wire were to continue, but the B field were not to continue, then the L would just be this length here. Let's see. And of course, the same cross product stuff applies as before. So probably pretty intuitively, the same way the point charge experienced a force in the upward direction in this situation, the wire will also experience a force in the upward direction. Alright, cool. So that is the effect of field on a wire. Now let's look at creating a B field. So we'll start with the most basic field from a point charge. So a moving charge produces a magnetic field, and we just have to kind of take the exact amount of field as a definition. So we find the B is equal to mu naught, so this is the vacuum permittivity, or permeability, I think. I might have mixed up the two, but it's mu naught anyhow, it's on the formula sheet. Q V cross R hat over 4 pi R squared. So this is for a point charge moving in space. And then you're looking at some random point, some radius r away. And you're wondering, what is the B field at this point? So, let's see. Alright, so first of all, the B field is proportional to the cross product of V cross R. So, well, okay, so this R is just for direction. That's R hat, so it has no magnitude. But in any case, that means for example, at this point I've drawn here, V is out this way, R is out this way. So if you do your right-hand rule, you'll find B field points out of the page. So let's see. For simplicity, I'll just look at the cases where you're kind of on the same level as the point charge, so to speak. So like on a circle, imaginary circle here. But for anything that's in front of or behind the point charge, you just have to look at the angle. So I guess I shouldn't have erased that just yet. So if this is your radius r and it's like some distance in front of the charge, then you look at this angle theta, and that's going to factor into your cross product and reduce the B field. But for anything on this radius, on this circle around the point charge, you're just going to see a B field pointing around this way. So let's see. I'll redraw this so you can actually tell what's going on. So that's behind, and this side is in front. There we are. So the B field points in a circle around the point charge as it's moving. Let's see. Yeah, that should be good. So then we'll introduce, Okay, so there is a right-hand rule you can use for this. This will also apply to the wire later. So this time, yeah, okay. So here, if you, okay, so if you use your right hand, point your thumb along where the charge is moving and curl your fingers towards your palm. Your fingers will curl in the direction of the B field. So as you can see, your fingers are curling like so. And that is the direction of the B field all around the point charge. Alright.
Is that for a positive point charge or?
Yes, this is all
Okay.
for a positive point charge. It'll be the opposite for a negative point charge. So, I don't know, you can use your left hand if you want, or you can just use your right hand and flip the result at the end. Either way. Alright. Now, okay, let's introduce a little thing called Ampere's law. So Ampere's law says that if we integrate B dot dl around a closed surface, it is going to be equal to mu naught times I, where I is the current enclosed. So to give you a picture of what this means, if we have a wire carrying some current I, then we are going to draw an imaginary random surface around it. So within the surface there is some cross section of the wire that's been like sliced. So if you integrate the B field along the outside of the surface, always going in a counterclockwise direction. Let me erase this just to show it goes behind here. Then that is going to be equal to the charge enclosed, or not the charge, the current enclosed times mu naught. So from there, we can directly derive the field resulting from a wire. So if we have this wire again, carrying some current I, and we want to know at some random point away from this wire. By the way, we're going to assume it's like an infinite wire. If we want to know what is the B field strength at this point, some radius r away, then we are going to use Ampere's law, which says the above. So because we chose a nice symmetrical surface, we can just say b times the circumference of this surface, which is going to be 2 pi r, is equal to mu naught I. And then you just move some stuff around and you find b is equal to mu naught I over 2 pi r. So, yeah, so essentially the reason this works is, let's see, so we already know just by like thinking about how field forms from a moving point charge that the field of this wire is just going to be going around in a circle like this. I guess more like this, yeah. So because of that, it's always going to be exactly parallel with this circular surface we drew. So we can just simplify the integral down to this. Alright, so that is field from a wire. So this is the same thing as above. You can use the right-hand rule. If you just point your thumb along the direction of current, your curling fingers will show you which way the B field is around it. Now, okay, before we go on, let's do a pretty common sort of practice problem. Two wires. So if we have a wire, ooh, bad wire. a wire here carrying some current I in that direction, and there's another one parallel to it carrying the same current in the same direction, and they are separated by some distance r. What force and in what direction will each wire experience? So we just need to pick a wire, let's say this one for now, the top one, and we're going to figure out what is the strength of its B field at this distance r, at the other wire. So to do that, we are going to use this formula here. So simply B is equal to mu naught I over 2 pi r. Then, to actually figure out the force on the other wire, we need to work out how much force that wire experiences because of that B field, which is all the way up here, IL cross B. So F is equal to IL cross B. So I guess I do need to specify the length of these wires. Well, we'll just call it length L. That's fine. So then this is IL times, alright, so I guess this is the cross product. So we just need to take a second to think about which direction everything points. So if you use the right hand rule, the curly one, so I shall copy and bring it down. Alright, so if we use this right hand rule on this top wire, we can find that the B field, its B field, points into the page. So I guess I ought to draw it like this, into the page down here. So then, using the right-hand rule again on the bottom wire, we'll find that the resulting force should point up, pulling the wires closer. So with that sorted, like they're clearly perpendicular, we don't have to insert a sine or a cosine or anything. So we can just directly plug in B. So we have mu naught I over 2 pi r. So in this case, because the i's are conveniently the same, we can simplify this to be mu naught I squared L over 2 pi r, and the force will be pulling the wires together. So this is the force on the bottom wire. This is the force on the top wire. So two wires carrying current in the same direction will be pulled together. Two wires carrying current in the opposite direction will be pushed apart. Alright. Now, okay, let's now, have you guys learned solenoids actually?
No.
Hmm.
I thought it was on one of our notes.
I think maybe if you say what it kind of is, I might be misremembering.
This is a solenoid, and there's current flowing
Okay,
around these
no.
coils.
Never seen that before.
Hmm.
Well, that's a lie. Current flowing around the coils. No, we've seen those before.
Okay, I'm just gonna say yes, I'll cover it. It's not that bad anyways. So, for a solenoid. So, drawing is hard, but, okay, so let's say we have this solenoid like this. So, current is flowing in this way, around these loops this way. So, now I'm going to draw this again, slightly differently. So let's imagine these wires are all like nicely, neatly packed against each other. So that's the top. And there's the bottom. So you can imagine, I'm not going to try to draw it, but the current at the top is going to be coming out of the page, and the current at the bottom is going to be going into the page. So the million-dollar question is, what is the B field at some point in the middle? So let's assume for a second that this solenoid is infinite. Then, actually, no, we don't have to assume it's infinite. So it's not infinite. It has some length L, and it has some number of coils N. So what we're going to do is we're going to use Ampere's law. So we're going to draw our surface like so. And with this surface, let's see. So the left and right sides will contribute nothing because we know that the B field should be pointing pretty much left and right at all points. And the top side, this side here, also contributes nothing because it can be shown that the field from a solenoid outside the solenoid is basically zero. I can, here, actually, no, I'll show why. So, let's see, what do I need? I need Gauss's law. Is that on your formula sheet? Yes? Oh wait, hang on. No, I don't need Gauss's law. I'm tripping. Ampere's law. Okay, so we draw some random surface out here. And we do Ampere's law, which, just to write it again, B dot dl is equal to mu naught I enclosed. So if for this surface there's obviously no I enclosed, so we know B dot dl must be 0. We can ignore the left and right sides because they're just pointing in the wrong direction. So here, actually, you can figure out, you should be able to figure out with some right-hand rule shenanigans that the B field should be pointing roughly to the left throughout this entire region. So the left and right sides don't matter. And then the top and bottom sides, well, then they must actually cancel out because for Ampere's law, you have to go around the surface. You can choose which way, it'll change the sign. But the point is, if you go left along the top surface, the top edge of the surface, then you're going to be going right along the bottom edge. So the amount of field along each edge must be the same in order for this to work out with no current enclosed. And that's important because we can draw this surface however we want. Right? I could extend this edge way down to infinity, and still the amount of B field on the top and bottom edges must be the same. Or I guess you could say the B field strength at the top and bottom edges must be the same. And that means the B field strength is uniform throughout the entire distance from the outside of the solenoid to infinity. And with a fixed amount of B field, so, well, okay, essentially you can't have infinite B field, so it's going to be very, very, very small. So, back to this surface up here, that means we can ignore this side, we can ignore this side, we can ignore this side. The only thing contributing to our Ampere's law here is this inside side. So then we do Ampere's law, B dot dl is equal to mu naught I enclosed. And so this just simplifies down to B times L, because we only care about the bottom side. And then that is equal to mu naught I enclosed, which is going to be equal to the I of the coil times the number of coils. So now if we move some stuff around, we'll find B field is equal to mu naught I n over L. And if you look at the formula sheet, you'll see they write this as Bs is equal to mu naught n, little n times L. It might be, oh, not L, sorry, I. So what they've done here is they've defined little n to be big N over L. So little n is the number of coils per unit length. So these are the same thing. So that is the strength of the magnetic field inside a solenoid. And you'll notice it doesn't depend on where you are inside the solenoid. So you could be down here or up here or right in the middle. The field strength is all the same. And then to figure out the direction of the field.
Does lateral distance matter? Like, does it matter whether you're closer to the center?
In reality, yes. It's going to be strongest at the center, and it's going to get weaker out to the sides. So if you were to graph it, this is like B field strength, and then if your coil is like starting here, then your graph is going to look something like this. And it's about half as strong at either like edge of the solenoid as it is in the middle. But for AP exam purposes, you don't really care, and you just always assume you have an infinite solenoid.
Okay, that's what I was looking for. Thanks.
Mm-hmm.
Wait, does this show up on the AP exam?
Solenoids? Yes. Okay, so then to work out which direction, you can use the right-hand rule. So it'll be this curly one. Here you're going to have to imagine, because I can't rotate this image properly, but if you point your thumb, like if we look at these top wires, you'll point your thumb out of the page along with the current, and if you curl your fingers, you'll find that the B field should be like this, and that means at any point in the middle, it's going to be pointing to the right. And if you do the same thing for the bottom wires, then your thumb should point into the page, and you'll find the B field does this, which means, again, in the middle, it's pointing to the right. So B field points to the right inside the solenoid, and then it points left outside the solenoid. I'll draw a better picture in a second. But another way to do this is you can, so actually now this hand is correct. So I'll bring this over here. So if you curl your fingers in the direction the current is turning, so that's this direction, then your thumb will give you the direction of the B field inside the solenoid. So let me quickly draw a little bit of a better picture of what the B field lines actually look like. So I'm going to draw it this style again. So once again, we have current coming out at the top, going into the page at the bottom. Your B field is going to look roughly like this. There should be bigger, but oh well. And there's just loops on either side. So, I guess you can kind of see why the B field outside is so much smaller, because this like set number of loops is all crammed in this tiny space inside, but then outside they have to spread out evenly from here to literally infinity. So the B field is basically 0. All right. Okay, so that is a solenoid. Let's see. Okay, so I think we've covered all the concepts now. Did I ever? I feel like no, right here. Okay, yeah. So we've covered all of the formula sheet stuff, and there should be all of the concepts as well. So this is just force on a point charge. This one is Ampere's law. This one is field from a point charge. This one is force on a wire. And then this one down here is field inside a solenoid. Alright, so now we've covered all the concepts. Now we're going to do some practice problems. Yay! So, first thing I want to cover is one I think Welch might not have actually done, or at least not very extensively, and that is a moving bar on rails. So, you have this here circuit set up. So these are stationary wires, and then the fourth side is a rolling bar. This bar is badly drawn. Oh my god. Okay, so this is a conductive metal bar that is free to roll. So the way I've drawn this, we're looking like top down at this. And let's see. So we need a voltage source over here. So there's a battery hooked up. So there's going to be some current running through this circuit in this direction. And then the bar is in a uniform B field. Let's say, so here, draw, this is the current. And then there's a uniform B field pointing into the page. And you have some length here, L. So what is going to happen to the bar? What force does it experience? Well, so we only really care about the bar itself. So the current is flowing downwards. So now we can just use the formula for force on a wire, IL cross B. So first thing, you're going to want to use the right-hand rule to figure out which way the force points. So if you do it the way I do it, your index finger should point down, your middle finger should point into the page with the B field, and then your force will point out to the right, your thumb. So force is to the right, and then to calculate the exact amount, you use exactly this formula, which actually I think covers everything. So there is the force on the bar. So in this case, it's going to shoot off to the right. Alright. I think if we can do the other type of this problem just yet. No, that's induction. Okay. So that is the moving rail. So if you flip the current, or if you flip the B field, then it's going to be getting pushed in this direction instead. Now, let's look at the motor. So, in this case, we have, how do I want to draw this? So let's say we have a coil, not a coil, a square coil that is positioned like so in a B field which shall point to the right. A uniform B field pointing to the right. And we have a current flowing around the coil in this direction. how will the thing spin? And how much torque, I suppose. So, I guess I should do the angled case for completeness. So I'll draw this again. But now the coil is at a slight angle. Some angle theta. And we still have this B field pointing to the right. Oops. Okay, so this is I downwards, and we'll call this length L, and we'll call this length here R. Alright, so let's look at the left side of this rectangle here. So we have a wire in a B field, so we're going to use F is equal to IL cross B. Now, L and B are not exactly perpendicular in this case. Oh, wait, hang on. No, they are. That's not the issue. Okay, no, we'll carry on like this for now. So IL cross B, everything is perpendicular. And if you use the right-hand rule, so point your index finger with I downwards, middle finger to the right with B, your thumb should point out of the page. So the force on this left part of the wire is exactly out of the page. And the exact amount of the force is, well, it's ILB. Now, the issue is for a motor, or for a setup like this, where this coil is pivoting around the center, we only care about the component of the force that is perpendicular to the coil. So drawing is hard, but it should be like this direction. Let's call this, do I have any coordinates yet? No. Let's call this F sub x. That is the part we care about. So if we look at this coil from above now, this is the way the B field's pointing. This is our theta, as before. Force is pointing this way, but we want to know what is this component here. So we can see that, yes, this is theta here as well. So this is going to be FB cosine theta times our radius r is equal to the torque. And of course, I guess you'll have to multiply by 2 because we only did the left side of the wire, but the right side of the wire is going to do the opposite thing. It's going to be pushing inwards and also helping. So now, if we substitute in what we got before, 2 times ILB cosine theta r is equal to torque. Alright. Yeah, and that should be the motor sorted. Alright. Now, what was the last one I wanted to do? Yes, okay, field along the axis of a circular wire. So you have some circular wire here. How do I draw this so it's intelligible? Okay, so we have an axis. Let's call this X. And then you have a circular wire, like so. So it goes behind on the left and in front on the right. And there is some current flowing around it in this direction. So what we want to know is at some point over here, what is the strength of the B field? You should be able to work out with right-hand rule the direction the B field is to the right. So to do this problem, we're going to have to know the radius of the circle you do. So, and if I set this up so that we have the y-axis here, and we already have the x-axis out to the right, so this is y, and then x is going to be, oh, hang on, I'll draw the entire triangle. So this is our beautiful little triangle here. The bottom face, or bottom side is x, left side is y, and then this hypotenuse we can call r for the radius from the point charge to some little bit of current or a little bit of wire. So now the total B field is going to be the integral of the horizontal components of all of the little bits of B field from all the little bits of wire around the circle. Because we know the component of the B field that points this direction or this direction is going to cancel out from all the things around the circle. So, no, not a surface integral. So we're going to integrate for little bits of charge. So we're going to use the scary formula, which is mu naught, where is it? QV cross r hat over 4 pi r squared. So with this, for direction, because we want to get rid of this cross product here. So if you use the right-hand rule, if we look at this little bit of wire at the top, the current is pointing out of the page. So if you use your right-hand rule for this cross product, V out of the page, R is just down along here, then your B field should point up this way, where this is a right angle. So this is our little bit of B field. So we only care about the component of this that points out to the right. So if we call this theta, and this is also theta, and we can replace this cross product with V, and that is going to be sine theta. And then, let's see, so we have the current, so we need to turn this QV into something in terms of current. So if we rewrite a little bit, integral of mu naught Q times L over time sine theta V 4 pi r squared. Then Q over T is our current, and then we just have L, which is actually going to be our DL. So I'm hand waving a little bit of math here, but it all works out. DL, and that is going to be our total B field. Alright, so then you just integrate around the circle, or, well, okay, so strictly speaking, this, well, hang on. Right. No, I'm skipping a step. So we have to get rid of this theta because, well, theta is annoying. We don't actually know theta in the problem. So we're going to replace it with, if we look at the triangle we've drawn, sine theta is the same thing as y over r. So y over 4 pi r cubed. And we need to integrate this dl. So you can further rewrite this, and it's going to be mu naught I y over 4 pi x squared plus y squared to the 3 halves. And then when you integrate around the circle, the integral dl just becomes the circumference of the circle, which is 2 pi r, or actually in this case the radius is y, so 2 pi y, since all of this stuff is constant as you go around the circle. So we can rewrite this to be 2 pi mu naught I y squared over 4 pi x squared plus y squared 3 halves is equal to b. So there you go. That's a pretty awful expression. But this is the sort of integral they might have you do on a free response, but they'll chunk it down into multiple steps for you and kind of hold your hand a little bit. So hopefully it's not too bad.
Can you scroll back up to like the
Mhm.
initial setup of the
Mhm.
okay. What's the V?
V is the velocity of the charge. So we started from the formula for field from a moving point charge, which is QV cross r hat, not hat, over 4 pi r squared. So essentially, I guess more rigorously, we started from B is equal to the integral of all the little bits of b, and that's all our little bits of b. And then we just rearranged until we got dl instead of db.
Uh-huh.
So
So it's the
essentially,
velocity of that one point.
yeah. So like you zoom in here, and then the wire looks like this, and all your charge or your current is flowing out of the page. That's not out of the page. Out of the page. So the v is going to be out of the page as well. And yeah.
Isn't V into the page on your diagram?
Right.
Never mind. I'm looking at it wrong.
So, I mean, if you're looking at like electrons moving, V is into the page, but then Q becomes negative and it cancels out.
Oh, okay.
Yeah. When you get down to, yeah, for pretty much all of magnetism, really, it's easier to just forget that electrons are moving and just think about positive charge and current.
Really quick thing. This is
Mhm.
like one of the beginning examples.
Mhm.
When you're setting like centripetal force equal to like the charge V cross product B,
Mhm.
I think you dropped a velocity in the numerator when you
Oh,
set
I
the radius
did. Yes, you're correct.
dB.